Okie dokie, folksies! Okay, so here's the three examples that we just left off with. I told you to go and try your answers to see if you get them correct and then compare them with mine. All right, so here are the three example problems, and I'm not even going to leave the screen. I'm going to make this very, very easy for you. So we're going to react each one of these with methyl magnesium bromide. All right, so a review of organometallic reactions in module number 2 very early on in the semester. Can you draw methyl magnesium bromide? I hope so. I hope at this point in Chem 252 you know what a methyl group is. If you do not know that a methyl group is a CH3 group, then we've got bigger problems at hand that we need to take care of, and I don't really even know how you made it to 252 in the first place. All right, so methyl, CH3, magnesium, bromide, MgBr. So this is the reaction or reagent that we are going to use in the reaction with the following three compounds. So this is the nucleophile that's going to come in and attack. All right, so that methyl group is going to attack the carbon of the carbonyl in each one of these cases. Because remember, that carbon in that double bond oxygen is okay, yeah, whatever. So that's the carbon that we have to watch out for. So the oxygen is going to be the electron sucker, and it's going to make a sucker out of that carbon, and it's going to rip those electrons up, making this a partial positive in each and every single case. That is why this mechanism works. So that negative is going to attack right there. That is going to be the addition of the CH3, and then this double bond breaks to a single, and we just have one single bond to that oxygen, and we can leave a negative there. However, to be honest with you, they are probably assuming that there is a proton that's at play, so we just need to go ahead and put the hydrogen there in that spot. Now, sometimes they do, sometimes they don't. You've got to be careful, but this one didn't say anything about an acid. I could leave it as an O-. If I do that, then that is a correct answer because they did not tell me that a second step is acid going to be there, but I'm making an assumption. I'm making an assumption that they probably know it's going to be. All right. All right. So in the second one, this is no difference. We will add the CH3 onto that carbon, and this is and that goes to a single. And then if an acid is present, then a proton will protonate that negative oxygen, forming yet another alcohol. All right, and then finally, this ketone to the right-hand side, we do the same thing. This is the carbon that's going to get attacked. That gets a nucleophile of a CH3, and then this double bond changes to a single, and that forms a negative oxygen. If I'm assuming that an acid is present, then I can protonate that oxygen yet again to form another alcohol. Do you see a common theme that's happening here, folks? It seems like every example that we have done has ended up with an alcohol group. And do you know what I can do from this point? I can now go back to any of those alcohol reactions, any of them, and I can pull any of those alcohol reactions back up, and I can say, hey, guess what? You remember all of those 25 alcohol reactions? Well, all of these are fair game at this point because all of these are alcohols. So I can protonate the alcohol to make it activated. I can get that alcohol to leave. I can substitute that OH group with another group. All of the alcohol theory can come back at this point, and that is how we're connecting the back end of the semester to the front end of the semester because we have come full circle at this point. All right. Now, the other thing that I also need you to kind of keep in mind here is that aldehydes and ketones are not the only ones, folks, that can react with Grignards. Now, we did not actually do too much of this in the top 1 carbonyls, maybe 1 or 2 examples, but that was about it. But I need you to understand that Grignards or any of these organometallics can be used in the top 1 reactions. Okay, so for instance, if I take an ester is a C double bond O with maybe some type of R group that is there beside of the oxygen. Those react with Grignards. All right, and they also react in at least 2 steps for the Grignard to take place. So if we had a Grignard, like we did in our last example, methyl magnesium bromide, that is the negative piece. That nucleophile can attack that carbon, and we form a CH3 group there. Well, that's going to that double bond, and oxygen is going to get those negative pieces. All right, but this is an ester, and that ester is a top 1. So in this case, oxygen can pull the wool over carbon's eyes and reform that double bond that is there. So we do not need the protonation step right there. The double bond reforms, and it forces that carbon to kick off a leaving group, and it that leaving group off. So the O and whatever is attached to that oxygen goes away, and what we end up with is a carbon double bond O. That was an alkyl group already to the left, and that is that one. And now we have just added on the piece to the Grignard, which is another CH3 group. So if we look at this functional group that we've just made, folks, this is a ketone at this point. So we have taken an ester and we have made a ketone as a product. And all of that is because top 1 can react with organometallics as well. The difference is the basics of the mechanism. In the top 1s, the double bond will reform and a leaving group leaves. And that is a good leaving group compared to the alkyl group that I have added on through the chain elongation step of the Grignard. All right, so top 1, do not rule them out. They react with organometallics just like top 2 does. The difference, again, goes back to the mechanism. Top 1s have a leaving group that will go away, bye-bye, see ya, come back another day. But top 2 keeps everything there, and it forces the oxygen to be protonated. All right? Okay, something else that we've also talked about, folks, is the acetylide ion. All right, so the acetylide ion was really heavily introduced in Chemistry 251. And this was a way that we elongated a chain at that point. So if we could create a C triple bond C that we called the acetylide ion, we could then take the acetylide ion, react that as a nucleophile, and elongate a chain yet again. And I want to bring that back because that's something that was introduced very early on, and this is now appropriate, just like the nucleophiles of the organometallics are appropriate. So these nucleophiles can attack the carbonyl of the carbonyl bond or the acyl group. Now, this happens just like everything else does, meaning if this is a carbon that is a double bond, and let's say that we have a CH3 right there, and then on this side, let's say that we have a hydrogen, so it's an aldehyde, and we are reacting a acetylide ion to this. Perfectly okay. That is the nucleophile, folks. So because that is the nucleophile, I'm going to take my starting reagent, and this is what it looks like. And guess what? I'm going to the double bond, and a site of attachment opens up, and that is where my acetylide ion attaches, because that is the nucleophile. All right? So this double bond does not reform. This is an aldehyde. It's a type 2. There's no leaving group. So we have to protonate it at some point, and this will form a alcohol because of that. All right? So this works just like everything else. There's no difference. However, I kind of want to go back and tell you how to make this. And the way that we did it is that if we had a carbon triple bond and there was an H on either side of that, this was called the acetylene gas, or ethine is the proper IUPAC. Acetylene, I know the ENE ending makes you think double bond, but acetylene is one of those common names that doesn't make any sense, but it's a common name because it's been there for hell and ever. All right, so here we have this ethine or acetylene gas, and we can react this with a strong base like an amine, and that will rip the proton off, and this will form an NH3 that goes away in the smell of a smelly cat urine smell gas, and then we end up with one of those protons that are ripped off. So that is the way that we make acetylide, and the acetylide ion reacts as a nucleophile at that point. Keep in mind, the only way that this works is if you have a hydrogen that can be ripped off, all right? So C, triple bond C, and let's say there's a hydrogen here, but on this side there's another methyl group. We can make this an acetylide ion. We can react NH2 to that molecule because we have a hydrogen on one of those triple bonded carbons that can go away, and then we end up with a negative piece right there. And that negative piece is the nucleophile, and this whole thing goes on to that molecule. So if that's what we added on, then that C, triple bond C with the methyl group all goes onto the structure, all right? However, if we do not have a hydrogen here, but on this side we have another methyl group like this, then the NH2 reaction will not work, and we cannot make a nucleophile that goes onto that. That was one of those things that we introduced in Chemistry 251 when we began looking at the alkyne reactions, because that's what that is, an alkyne, a carbon triple bond carbon molecule. Again, foundation, build up on, very, very old topic, talked about in a previous course in a different semester, and now it's coming back to haunt me thinking that I'm the expert on triple bonded reactions. But that was basically a review of what we did. Now, with that said, I'm going to take it another step further. So this is a nucleophile. And it seems like the nucleophiles are working the same way every single time. And that makes sense because it's really a mechanism that we're learning. Who cares what the nucleophile is, folks? I don't care what it is. So for instance, if this was a carbon with a triple bond N, all right, well, the same thing's going to happen. Carbon is going to get attacked. That carbon, we're going to have a C triple bond N that adds onto a molecule. That C triple bond N forces the double bond to break. That oxygen gets the hydrogen from a protonation step. This is the same exact thing. What I'm trying to get across to you is that this piece doesn't matter. A nucleophile is a nucleophile is a nucleophile. It does not matter what it is. So anything that is negative will go in and attack that carbon because that is what this mechanism says happens. So I keep talking about organometallics. That's not the only reactions that can go forward. It's just an example because that gives me a nucleophile to work with. And then we talked a little bit about acetylides. That was just a review to go back and think about what the acetylide was back in the day. It's still a negative. It's still a nucleophile. And look what happened. It went and it attacked that carbon right there, and the double bond went. Any nucleophile will do the same thing no matter what it is. So do not let these questions trick you, folks, because that is what they're going to do. They're going to throw in these nucleophiles, and these nucleophiles you're going to think, well, I've not done an example like this. Well, you don't need an example like that one. What did I say? It's like a math course. I can show you examples and procedures. We learn the procedure. We do not memorize examples. So the procedure here is taking a nucleophile, negative, and attacking the carbon of the carbonyl. That is what we're doing. And that double bond will break, and we get this addition, and we get the protonation step. That is what this is all about. All right? Okay, so with that said, there's another kind of tidbit of information I don't want you to get confused with. And each time we've talked about adding H+. And this was the protonation step. We said that this was a very good way to put a hydrogen onto the oxygen of the carbonyl. That's not the only way that we can do it, though. So another way that we can protonate it is take a ring. So now I'm blending in more of the benzene and disubstituted benzene reaction lectures. We can take this ring that has a nitrogen in it. Do you remember what that was called? This nitrogen has a hydrogen that's right there. It's got a free set of electrons that's right there. This is involved in a delocalized network. So therefore, this thing can act as an acid. It is another form of an acid that people typically get confused with because they look at nitrogen and they think, oh, this is a base because it's nitrogen. No, it's not a base. This is acting as an acid because that is a proton donor. That is another way that they can try to trick you in these questions. Folks, this structure here was called pyridinium, right? This is a pyridinium ion. When this nitrogen loses the hydrogen, we have this molecule that's left over, and that's the pyridinium ion. So pyridine can be used in these reactions to form an acidic environment, and that will be the proton supplier to the reaction. So very weak acids sometimes are used. These are very weak, as you just kind of heard me say, but this is a nitrogen, it's supposed to be a base. No, that's not true. There is a hydrogen that's there that can be spit off, but it's very, very low quantities. And because of that, this is a very weak acid. And the reason is because I would want to use something like this so it does not react with other functional groups that might actually be on the molecule, all right? So in other words, let's say that I end up with CH3, CH2, CH, and then here an O that needs to be protonated, and then off of this CH group I have added a nucleophile, and that nucleophile is maybe this piece, right? This is the nucleophile that I have added on. So if this is where I'm at, and this is a negative charge, I run the chance of reacting that triple bond. And the reason is because this is an alkyne. And alkynes, which are triple bonded molecules, can react with things like hydrochloric acid. My triple bond breaks, two sides of attachment open up, hydrogen goes on one side and chlorine goes on the other. Any triple bonded reaction is fair game at this point. So what I want to do is I want to stay away from those super strong acids because they will target that triple bond, or they will target the incoming nucleophile that I'm adding onto the molecules. And I do not want competing reactions here. I want my triple bond to stay until I'm ready to do something to it. So one of the ways around that is to use a very weak acid, and that weak acid could be something like pyridine. And the reason that they are using this as an alternative is because it is very, very weak. And that is good because just a little bit of proton is going to be spit off, and that proton will definitely go there on the oxygen, and it will keep my triple bond at play. All right? Okay, so with that said, I'm going to leave you with another reaction here, or example, and we'll talk about these in the next video that's coming up. So the example here says, make the following compounds using any form of an acetylide ion and any other starting product. And it gives me 3 of these examples: 1 penton 3-ol, 1 phenyl 3-butan 1-ol, and 2 methyl 3-hexane 2-ol. All right, so those are the 3 examples. It looks like they want me to make those, so I'm going to have to use an acetylide ion in some form or fashion because it tells me to do that. And I've got to come up with a reaction scheme in order to figure out how I can get to this point. So once again, try these 3 examples on your own. See what you can come up with, and then in the next video, push play, and then double check your answers to see how far you got. Did you get the correct answer? Did you get the wrong answer? Did you even know what you were doing? So that's kind of the thing that I want you to do. I think it will help you for these problems to try them on your own first, and then come back to me to figure out what you did wrong and why you chose what you did that you did wrong. I think that helps you out in the long run much, much better than just pushing play and then just taking my word for it and jotting down some notes. All right, so there's the example problem. Good luck on those 3. Push play whenever you're ready, and I'll be here and we'll go over the answers together.